When we say that the momentum, heat, and mass transfer are analogous, we are not saying that they're the same physical process. If you think that, then you will confuse what is being transported. What we mean is that they share the same mathematical structure. The physics is different, but the equation has the same form. That form only makes sense if we are very clear about two things: what is being transported and what the units are. In all three cases, our quantity of interest is flux. Flux does not mean how much. Flux is the rate of transport per unit area per unit time. Something crossing over a surface per area per time, always. Our three areas of interest are momentum flux, mass flux, and heat flux. For momentum transfer, what is being transported is not velocity, but momentum. The distinction between velocity and momentum matters. Momentum flux appears as a shear stress. Shear stress is experimentally proportional to the velocity gradient. Shear stress is equal to viscosity multiplied by the shear rates, which equals force over area. And this is equal to the viscosity multiplied by that gradient. That velocity gradient is equal to that shear rate. How do we know that? Well, this viscosity is a constant between both equations, meaning that these must be equal in some aspect. And so that's how the shear stress is proportional to that gradient. If you divide that viscosity by density, you will find that the units, kilograms, meters, seconds, kilograms, meters cubed, equal meters squared over seconds. Those units tell us something. Momentum spreads through space through a diffusive process, meaning that momentum diffuses. For heat transfer, what is being transported is thermal energy, not temperature. Heat flux is equal to units of energy per unit area over unit time. It is proportional to the temperature gradient. The proportionality constant, thermal conductivity, multiplied by that temperature gradient, gets you heat conductivity, heat convection, heat flux. When you take that thermal conductivity and you divide it by density and heat capacity, you get thermal diffusivity. The units for this are meters squared per second. These units are the exact same as when we discussed momentum transfer. This tells me that thermal energy spreads through space by diffusion in the exact same mathematical way as momentum. For mass transfer, what is being transported is species mass. Mass flux is proportional with a concentration gradient and has a proportionality constant of mass diffusivity. The units for mass diffusivity are meters squared per second. This once again tells us that species mass moves through space via diffusion, molecular diffusion. So where is the analogy? Well, in every case, flux has a gradient with a concentration-like quantity and a proportionality constant that has units of length squared over time. The physical meaning changes from momentum to energy to species mass, but the mathematical structure does not. Momentum diffuses, heat diffuses, and mass diffuses. Same structure, different noun. So what is Fourier's law? Well, Fourier's law is the equation, the constitutive equation of heat conduction, often written as Q. And heat conduction is written in terms of heat flux. Now, as we previously learned, heat flux is the energy transfer per unit area per unit time. All of these have their own units. Oftentimes, energy is in joules, area is in meters squared, and time is in seconds. So if we take that, we can transform it into watts per meter squared, which is joules per second per meter squared. The moment that you see heat flux, you should immediately be thinking per unit area, per unit time. If not, you'll be in a lot of trouble. So now let's write out Fourier's law. Most people might say Fourier's law is Q equals negative K times dVx over dy. That is not Fourier's law. Why? Because this is not Q. This is heat conduction. This is not K. It is thermal conductivity, a proportionality constant. And this is not dVx over dy. This is the gradient of temperature, or a temperature gradient. A temperature gradient is not just a temperature. It is the rate of temperature with position. A temperature gradient is not temperature. It is the rate of change of temperature with position. This temperature gradient has units of Kelvin per meters. We know that heat flux must have units of watts per meter squared or joules per seconds per meter squared. In this case, thermal conductivity must have units of watts per Kelvin meter in order for it to transform into watts per meter squared. These units are not decorative. They are enforced by dimensional consistency. Now, as you see, there's a negative sign in front of Fourier's law. What is that there for? Well, heat flows in the decreasing temperature. Oh my gosh. Now, there is a negative sign on Fourier's law. This is there to ensure that the laws of thermodynamics are being followed, specifically the second law. You see, heat flows in the direction of decreasing temperature. So if temperature is moving in the positive x direction, heat flux will move in the negative x direction. The negative sign is there to ensure that heat flow will move from hot to cold. Now, thermal conductivity and thermal diffusivity are related, but they are not the same thing and should never be used interchangeably. Thermal conductivity is how the temperature gradient affects heat flux, as we see here. It is heavily affected by the type of material and has units of, as we see, watts per Kelvin meter. Thermal diffusivity, on the other hand, that is used to show how temperature disturbances propagate through a material. Thermal diffusivity also has units of meters squared per second. It is equal to the thermal conductivity over the product of density and heat capacity. These units should tell you immediately that is related to the process of diffusion through space and time. In summary, heat conductivity is how much heat flows, while heat diffusivity is how fast temperature spreads. Heat conductivity is a flux law coefficient, while heat diffusivity is a transport time scale parameter. Same phenomena, different questions, different nouns.